Okay. So, as I just said a second ago, and probably those of you who have just walked in noticed, I am not Yulia. I'm Dr. Dave. It's going to be your sub today. So because I haven't been here until this point, I have no idea what's going on in your class. So can you all help me out? What have you guys been talking about? Yes. Just talking about U substitution. Excellent. Okay. No, that's great. That's a thing. We're going to talk about that here in a second. So somebody else, what was U substitution all about? Can someone remind me? Like I would give you, well, I wouldn't, Yulia would. She would give you a problem, and what would you use U substitution to like complete? Yes, ma'am. I love it. Okay, so U substitution undoes the chain rule. Okay. So now I got to ask about the chain rule. What was that? Someone remind me what the chain rule was. A technique of something. So you would use maybe the chain rule, or another example would be the power rule. You use these things to take what of a function? Take a derivative, right? So, sort of the theme in this class so far, right? You've had these techniques of, technology, differentiation, which you can think of as taking derivatives. Okay. Now, this U substitution, this thing that undoes this chain rule, what technique was that an example of? I think integration. Yeah, she was exactly right. Sorry, completely. No need to apologize. That's great. Yeah. So, okay. So we've got differentiation over here and integration. So taking integrals or taking anti-derivatives. And so that anti-derivative thing is kind of telling. What does that mean about these two procedures? How are they connected? They're inverse, right? So integration and differentiation are inverse processes. Very nice. Okay. So I think I'm all caught up. You guys have been talking about differentiation, integration. We know that these things are opposites to one another. So if I take a derivative, then an integral, those processes cancel each other out. Okay. You've been talking about U substitution, okay, which is a process that undoes this chain rule. Okay. So let's just kind of jump right into an example. So suppose we wanted to calculate the integral of x to the 5th times x to the 6th plus 20 dx. So indefinite integral of this function. Anybody want to take a stab at how we would go about this? Or an attempt. It doesn't need to be that violent. Yes, sir. Okay. So talk to me real quick. Why? So, okay, I think we want to grab this U. So U equals x to the 6th plus 20. Now, why did you choose that? Well, okay, let's see if I can grab some of that. Yes, sir. Very nice. Okay. So this following function that we want to integrate, x to the 5th times x to the 6th plus 20, that looks like the result of doing the chain. Okay. I forgot a piece here. I want that to be to the 8th power. This x to the 5th on the outside as up to maybe a constant, the derivative of what's happening on the inside of this raised to the 8th power function. Does that kind of make sense what I'm saying? So typically your choice for U, want to do a substitution, will be something that is inside of another function, that is composed with another function. And then hopefully you'll get some cancellation when you substitute in your dx and so on and so forth. All right. So somebody on this side, once we have u, what's the next thing we do? Yes, ma'am. Okay, so how would I do that? Excellent, excellent, dx, okay? And that dx there is important. You can kind of think about it, like how I like to think about it is these d whatever variables represent like a little error in your measurement in that variable. So it's like, how do I get the error in the u? I take the error in x and multiply by how it's changing, this derivative piece. So then what happens next? Yes.
Well, what we need to do is convert the derivative of u to the given problem by finding 1/6 of du to get 1/6 of du equals x5 dx.
Outstanding. Okay, 1/6 x5 times dx. Okay. And so the point of this, right? Because we want to start replacing things that we see in the integral, things that we're manipulating off to the side. So u, we can replace with that x to the 6 plus 20. And then x to the 5th times dx, we can replace with this 1/6. Okay? So then what's my integral going to become? Well, this is our integral. What's our integral going to become? Once we start replacing stuff. Yes, sir. 1/6. Perfect. Okay. So what's happening here? So this x to the 5th, oh. Draw. X to the 5th and dx is getting replaced with the 1/6 du, according to what's going on here. And x to the 6th plus 20 is getting replaced with u, because that's what we called u originally. All right. Everything good there so far. All right. So cleaning this up a little bit, we can write this as 1/6 integral u to the 8 du. And how are we going to find an antiderivative u to the 8 du? Is that an antiderivative we keep in back pocket? Yes, ma'am. Okay, so we get a u to the 9 over 9. And anything else? Plus c. Okay, looks great. Looks like we're missing one little thing. Does anybody see what I'm seeing? The 1/6 out front. But other than that, perfect. Excellent, right? And so what are we doing here to get this u to the 9th over 9? Product power rule to make these. So how does the power rule work? Bring the exponent down, subtract 1 from the exponent. Integration is the opposite. So add 1 to the exponent, divide by the new exponent you get. All right. Any questions there? Okay. So we're done, right? No. What's left? Have to sub u back in. So what's my final answer going to be here? So let's see, 6 times 9, we'll get 1/54. Okay. Then I'm subbing back in u, x to the 6 plus 20 to the power 9. Oops, plus calendar. No, plus c. All right. How are we looking? Anybody see any issues? Okay. All right. Any questions with this example. All right. Am I okay to erase what is on the whiteboard here? Excellent. Thank you. Okay. So let's look at another example. How about integral 2x cosine of 2x dx? Actually, I want to change my variable name. Instead of x, what variable name should we use? Q? I like it. Okay. So 2q times cosine of 2q with respect to Dairy Queen. Okay. So what are we thinking for this problem? Typically, when we've seen something like this, or I'm only assuming because I'm not here all the time, what techniques would you normally use to go after this integral? So yes, keep. Okay, so there's something we need to do with this 2q hanging out front, okay, but ultimately we will be having an integral cosine. So what I was thinking was pretty much all you've done at this point, right? Other than remembering antiderivatives would be the substitution method. Okay. So if we tried to set up a substitution, how would you try in this case? Does that kind of make sense what I'm asking? Like if we wanted to use the techniques we just used for the last problem, how would they fit into this?
Either two, that's like after the cosine.
Yeah, so you might try something like u equals 2q, because this 2q is being plugged in to cosine. Okay. So then when we calculate the derivative of u, what do we get there? Du. 2, and then there's another piece there. dq. Okay. Okay, so we get u, we get du, and then typically what comes next in this substitution method?
We convert from two, we solve for dq.
Yeah, solve for dq. So dq is going to be 1/2 du. It's fun when your variables rhyme. And then after substituting, what's going to happen? The dq gets replaced with 1/2 du. All right. So we'll have integral 2q 1/2 du. And then 2q gets replaced with u. What's going to happen next? So we can move the 1/2 out, right?
See the first formula, we can see, say that we equals two, so we can substitute q.
Actually, yeah, we don't need that two anymore.
Oh, yeah.
Make the q. Two q equals u over two.
That's excellent. Excellent. So yes, we could do this. We could use this to substitute q equals what do I want? U over 2. Excellent. Okay. So in doing that, what's going to happen? Oops. Not eraser. These are going to cancel. The 2 and the 1/2. Okay. Then what do we say? We said q gets replaced with u over 2. So we're left with integral u over 2 cosine u du. Very good. Okay. Then what do we put this one?
So we have two q.
To plug in the 2q for the u, that kind of brings us back to where we started originally.
We can just derive.
So at this point, okay, how would we integrate if we wanted to integrate this?
Well, first of all, we need to.
No, you're good.
U over. Or what you do is not one with it. But you should be multiple, you over to be multiplied. Do we need to integrate it at all?
So we do need to integrate this U piece because it is part of our integrand and also the variable of integration.
U over two stays.
So yeah, but the U over two still depends on U. So that's part of like the function which is being integrated. Great. U is changing as this variable of integration.
I know, but we can, it's kind of stayed as it is for now, right? And then we just. Will solve.
So yeah, long story short, we can't really move forward at this point. It's kind of the story that I was trying to tell. Is using the substitution, we kind of hit a brick wall. So we're up to something similar that we had at the beginning here, where we had U times Q times cosine of 2Q. Okay. We ended up with something, a variant of U times cosine of U. So the idea here is if, say, this inner part was Q squared, we would have gotten the right cancellation and the substitution rule would have worked. Okay. So what we're going to do now is introduce the next integration technique. So am I okay to erase what's on the board here? Okay. Which is called integration by parts. So in this spirit of all of these integration techniques being something that more or less undoes a derivation technique, integration by parts is going to be the integration technique that undoes the product rule. So kind of like the chain rule, or substitution rule undoes the chain rule. Integration by parts is going to be what undoes the product rule. So the setup kind of makes sense so far. Any questions at this point? So real quick, somebody remind me, how does the product rule work? I take the derivative, so I'm going to let someone else answer this, but I appreciate you. Excellent job today. So I take the derivative of f of x times g of x. How can I write that in terms of f, g, and their derivatives? Does anybody remember how this works? Yes, ma'am, in the back. Yes. Outstanding. F prime of x times g of x plus g prime of x times f of x. Excellent. Okay. And this is our product rule for differentiation. Any questions there? So let's try something real quick. Let's integrate both sides of this equation. After all, we're talking about integration techniques. So let's introduce some integrals and kind of see what happens. X prime of x plus f of x g prime of x dx. Okay, so started with what was there before, then just took an integral of both sides with respect to x. Now, what's going to happen over on the left side of this equation? I'm taking a derivative, then right afterwards, taking an integral. So we'll get fxgx. What's going to happen is the integral and the derivative are going to cancel one another. That is, what we'll get on this side is f of x, g of x, integral. And so what I'm going to do here is I'm going to break up this stuff on the right into two integrals. But we'll get the following. Any questions there?
Sometimes just the integration of that entire thing is equal to that equation.
Yeah, so this is what you're asking, level below, right side. Right side.
No, I think is f of x times g of x.
Equal to everything on the right? Yes.
Okay, not the integration of f of x times.
So what this is was the integration of the derivative of f of x g of x. That's why it ends up just being.
So it all reduces. I'm confused. Now I'm completely confused.
Sure, that's no problem at all. So kind of the idea here, let's sort of back up to a very simple example. So let's say I have the variable x and I add 3 to it. What's going to happen if right after I add 3, I immediately come back and subtract 3? It'll reduce to what? To just x. Outstanding.
The right side of the middle of the second line. Right,
Okay.
reduces to f of x times g of x.
So no. What? Well, yes, because of equality. Two operations, kind of like plus and minus, and undo one another.
Yeah, my main question was if you were at. Oh, because obviously it all reduces to that.
All good?
I think I'm getting it now. I was mainly wondering if there was supposed to be an integration sign.
So yeah, right here, there is not supposed to be an integration sign because it canceled with the derivative sign right there. Yes.
Something and integrated. Again, like what's the point of adding 3 and then deducting 3 right after?
So the idea here is what we're trying to do is an excellent question. So what we're trying to do here is even though we're doing operations that don't give us anything new, they may potentially give us a new way to write what we're dealing with. So ultimately, what's going to fall out of this is our integration by parts formula. So what we're doing is we're kind of taking the product rule, doing some manipulation. So that presents us with, if we have an integral of this form, we can use this formula to kind of solve. Does that kind of make sense? Yeah, I think it'll make more sense once we kind of move on a little bit, but excellent. Excellent questions. Any other questions there? Okay. So how does this move forward? Okay. What's going to happen is we're going to subtract away. Which one do we want to subtract? Yeah. Subtract away this integral to the other side of our equation. So that ultimately what we'll get is the integral of f of x times g prime of x dx is equal to f of x times g of x minus the integral g of x f prime of x dx. Okay. It's all going to make sense here in a second. But is everybody kind of okay with how we got from just the product rule to this formula at the bottom?
If you realize that you're gonna.
Any questions? Yes, ma'am.
Icons.
Okay. So what happened was good. Sorry. No, you're good. So what happened was there was an integral. The second line. We started with that first equation of f times g equal, and then took an integral of both sides. So what happened here was in the second, third line, going from second to third, because we were taking an integral of something that is a derivative. So first take a derivative of this object, then an integral. That's where we lose the integral. And so once you lose that integral, it's just this object for the rest of the calculations. And so that's why it just still is f of x times g of x here. Excellent. Any other questions? Okay. Is it okay if I erase some of the stuff at the top of the board here? All right. So what is the usefulness of this pink equation that we have down at the bottom? Okay, so we've got integral f of x times g prime of x dx equals f of x times g of x minus integral g of x times f prime of x dx. Okay. So if you remember from the substitution rule that you all just went over, we make a change of variables in this procedure. We look for a function in our integral and replace it with u equals to make our problem a little bit simpler. So for integration by parts, because we are ideally undoing the product rule, there should be two functions of interest. So ultimately, we're going to make two substitutions. That is, one of these substitutions is going to be u equals, and one is going to be v equals. Okay? Everything good so far? We'll take, and it really doesn't matter which one you take because it's kind of a symmetric problem. U equals f of x and v equals g. Remember way back in the beginning, looking at the product of f and g, because those are going to be the substitutions we're making. One's for f, one for g. Everything good there so far? So when we go forward and calculate the differential du, if u was f originally, what's du going to be? Prime. F prime times dx. And then times dx. Now you're good. No need to apologize. Times dx. And then similarly, dv is going to be g prime of x dx. Okay. Everybody still? So then what's going to happen is we'll start replacing the relevant pieces. So f of x, we renamed u. So u, g prime of x dx, well, that's dv is equal to u times v minus integral. And then what's this one going to be? G of x times f prime dx. What two objects are those? v du. Outstanding. Okay. Everybody okay so far?
Wait a minute, that's weird. The what? What? No, make any sense. Never mind. I did that. Big benefit.
I say like 20 of those things a day, so don't worry about it. It's all good. Okay. Yes, ma'am. Sorry, I saw your hand come up. You good? Okay. So this is the worst part of this, is you have to make sure your U's are round enough and your V's are pointy enough. So what's the point of all that? The idea here is this formula at the bottom is going to be our integration by parts formula. So how is this going to work? What's going to happen is you're going to be presented with an integral that looks like something on the left. The some function u times a derivative of another function. And then what you'll do moving forward is reduce this problem according to the variables u, v, and then ultimately v and du. Okay. So how these always start off is the burden is on us to determine what's going to act as our u function and what's going to be our dv function. So the first things we need to do, pick u function, and then pick dv function as well. So we'll look at some examples here in a sec, but any questions so far?
How does this help us find the integral of the entire formula?
You'll see here in a second. Yeah. So at this point, it's kind of just like the abstract machinery stuff we're putting together, but you'll get to see the meat and data here. Yeah, essentially. Yeah, it's a wonderful way to describe mathematics in general. Yeah. Kind of just play around until stuff is useful. Excellent.
The obvious.
Yes. Any other questions there? Okay. Am I good to erase what's going on here on the board? Okay. So let's come back to our integral of 2q cosine of 2q dq. So using this new technique, the burden is going to be on us to determine what is the u variable and what's going to be our dv variable. So I'll pretty much walk you all through this first one and then give some kind of like pro tips along the way of like, what's the good choice of u, what's the good choice of dv, so on and so forth. So we're going to take u equals 2q and dv is going to be cosine of 2q dq. So that's all. Determine what u is, determine what dv is. And so when you pick dv, d, whatever the variable is, has to come along for the ride as well. Okay. So if u is equal to 2q, what is du going to be? 2, and then need one more thing. dq, outstanding. So u is equal to 2q, then du is equal to 2dq. All right. If v is equal to cosine of 2q dq, dv, thank you, yes. Then what must v be equal to? Okay, so yeah, we're going to have sine of something happening. And it's going to be sine of what? 2q, I agree. And is there anything else that I need here? A 1/2 out front. So that's an excellent point. Typically, when you do an indefinite integral, you do need a plus c. Yeah, exactly. We're going to do it at the end. Yes, sir. Exactly. So why is the 1/2? E represents a function that when you take its derivative, you get dv. So when you take the derivative of 1/2 sine of 2q, when you do the chain rule, you're going to get a factor of 2 from the inner piece. And then times cosine of 2q. That looks smushy and awful. I'm sorry. 1/2, 2 from derivative of the inner, and then cosine of 2q. Is that okay there? Excellent. Any other questions there? All right. So how does our integration by parts formula work? Based on the choices we made, we're given the integral of the u dv part. So this is the part that we're given here. Everybody kind of understand what's going on there. So what we change it into is the uv minus integral of v du. And so I've had some students give me the device where you think of this as ultraviolet minus integral of voodoo. And I've always remembered that one, so I like that one. Careful when you use it though, because you don't want to bring too many demons on everybody. All right. Any questions there? Don't quit my day job, right? Okay. So now this was the whole u dv v du renaming. Because now we can just take all the pieces we have up here and replace them accordingly. So for example, u times v is going to be 2q times 1/2 sine of 2q minus integral v 1/2 sine of 2q and then du, which is 2 times dq.
Yeah. Okay.
So no, not in front of the 2q, because that's actually from, remember, that was from there was a derivative followed by an integral, and those guys or folks canceled out. Yes, sir. So dv was cosine 2q du. So then to get v, you have to integrate it. So I think I'm good there. The benefit is once we get done with all this, we can check our answer by taking what we have and then taking a derivative. We'll kind of see at the end there. But I think everything is good at this point. U is 2q, so derivative du equals 2 dq. dv was cosine 2q dq. So then v, take an integral of that, we'd want 1/2 sine of 2q. I think everything is good so far. Maybe not.
No, I think the thing man.
Okay,
Well, you can review.
we will hear in a second. Yes, ma'am. Yeah, so the integral u dv part is kind of what presented with the range. So the u dv represents the purple integral there. So it's kind of like u matches up to q, then dv matches up. From that, we get our du and v, and then kind of fill in everything. All right. Any other questions? All right. So we're going to get some simplification. So what's going to happen here? 2's will cancel. We have q times sine of 2q minus 2's cancel again. Integral sine of 2q dq. Okay. Integral sine 2q dq. And how would we go about calculating that?
Well, we just convert the chain rule again. I mean,
Yeah, we kind of already did this, right? But for cosine. So q sine of 2q, okay, minus. So antiderivative of sine is going to be minus cosine, okay? So what do I need to do to correct? Because I'm doing a chain rule. Outstanding. And then a plus c. Kind of running away from me, plus c. I'm going to erase some stuff and rewrite this again here nicely. But are there any questions at this point? And so that's really the purpose of this integration by parts is you set up through this formula, you still have a single kind of integral to calculate, but hopefully it's one that after making your u and dv choices, it's a little bit simpler than the one you started. Okay. Any questions there? Am I okay to erase some stuff just so I can write this completely simplified? So essentially the red stuff is what I'm going to erase. All right. So we get done at 110. Okay. Thank you. Okay. What are we doing? Equals. So Q sine of 2Q plus minus minus becomes plus. So 1/2 cosine of 2Q plus C. Everything look okay there.
Is that the final answer?
So this is the final answer. That is correct. Okay.
You know,
Yeah. Hey, it is doing its best, but you know, it could do better. But how can we take this final answer and sort of check ourselves that we got the right thing? We could derive it, take a derivative of it. So if we take a derivative of it, this answer that is, and recover our original integrand, the thing we're integrating, then we know we did this process correctly. So let's do that. Derivative, ooh, careful, with respect to Q, of Q sine 2Q minus 1/2 cosine of 2Q plus C. Okay. So looking at this first part, what am I going to get for the derivative of that piece?
Find this. That's 2Q sine.
Perfect. So I'm going to need to do a product rule. Okay. So we can think about this as sine of 2Q times derivative of Q, which will be 1. Okay. Plus Q times, perfect, 2 cosine of 2Q. All right. Yes.
I understand what you did here.
Oh, just the product rule for the first piece. Yeah. So yeah, we still have a ways to go. We haven't finished this derivation yet. Excellent. Thank you. Okay. Everybody good with that first piece? Now, what about derivative of this piece? What are we going to get here? So 1/2 comes along for the ride, constant. Nice. Derivative of the inner. So derivative of the inner is just 2 from the 2Q. And then derivative of cosine, outstanding. Minus sine 2Q. Okay. And then how about derivative of that plus C? 0. Okay. So in simplifying this, we get a sine of 2Q plus 2Q cosine of 2Q. 1/2 times 2 is 1. Even I can do that. Times minus. So minus sine of 2Q. And then what's going to happen? Sine of 2Q and minus sine of 2Q cancel out. And we're left with 2 cosine of 2Q. And victory is ours. So any questions? Okay. So I think we might have time for one more example. If not, we might not finish it, but that's okay. So any questions here? Now, word to the wise, pro tip. Sine of k times x, cosine of k times x are usually good choices for dv. So you'd want to take a lot of the times, if presented with a problem like the one we just saw, dv equals cosine of some multiple of x, or dv equals sine of some multiple of x. And while I'm up here, the other good choice, because this is related to the example we're about to do, e to some multiple times x is also a good choice for v. Good choices for you. Ln of x or powers of x are also good choices of you. But you all will talk a little bit more about this in your next class as well. Okay. Just real quick, let's look at the integral 2 to the x times e to the 3x dx. These integration by parts problems always start with choosing what is u, what is dv. So based on our very limited kind of toolkit we have here, what might be a good choice for u? What might be a good choice for dv? Yes, sir.
Well, you should do that.
I agree. Let's take u equals 2x. And then what about dv? What should that be? Do we see any of our usual suspects? Yeah, so let's take e to the 3x dx as dv. So after we get u and dv, what comes next? What do we du? Well, we find du. And so du is going to be 2 times dx. And we integrate our dv to find v. And so you can check real quick. If you take a derivative of 1/3 of 3x, that derivative e to the 3x. 3's will cancel from the chain rule, and that's how you recover this e to the 3x. All right. So integral is presented in the form u times dv. We make the change according to ultraviolet minus integral of voodoo. Everything okay? So then u is 2x, v 1/3 e to the 3x minus integral v 1/3 e to the 3x times du, which is 2 dx. Everybody okay there? So simplifying a little bit, we'll get 2/3 x e to the 3x minus, pulling out all of our constants, 2/3 integral e to the 3x dx. And so the last this integral 3x dx. And what's that do? Perfect. Exactly what we did earlier up here. We just get a factor of 1/3 when we take this integral. So 2/3 x e to the 3x minus 2/3 times 1/3 e to the 3x, and then plus c for calendar. Okay. C plus c. All right. Any questions there? So yes, so we can do a further reduction, write this as minus 2/9 e to the 3x. But I'm out of space and we're out of time, so we will call it there.